problem 20.9. So we want to find all the maximizers of the function of this form, this ratio here. So we have seen this question in class. The idea is that we convert this into a constraint optimization problem and derive the Lagrange condition and then solve for that optimal point. Okay, so now the question is to minimize the maximizer ratio. Is the same as minimizing the numerator and the constraint that the denominator is equal to some constant. So let's just first factor out these two. So there are two on every one of them. So I just divide two of them. So I require the denominator to be equal to 1, and I want to minimize the negative of the numerator since we're trying to maximize the numerator itself. So that's this, minimizing this, and this can be written as a quadratic form of x1, x2, where this Q matrix is just determined by those numbers. And the constraint is that this is equal to 1. Okay, so we call this the Q matrix and this the P matrix. And then remember that once we have that, we construct the Lagrange function where the objective function is this, the constraint is this minus 1 equals 0. So that's why we multiply lambda to this, and then take the gradient. We'll get the Lagrange condition, which is this and then this. Okay, so what this implies is, remember P is identity, so that this one just means that x is a unit vector, and this, when we move this term to the right and multiply both sides by the P inverse, and then we get this. So this just means that x is not just a unit vector, but it's also a eigenvalue of the matrix negative P inverse Q. Okay, we have the P and Q, so we just compute that. That's just the inverse negative P inverse times Q, and we're looking for the eigenvalue eigenvector of this matrix. So it's pretty easy to compute that the eigenvalue of this is the root for this quadratic function right here. That's the determinant of this. So we rewrite this lambda I minus this matrix, compute the determinant as equal to 0, and then we get a quadratic function of lambda. Okay, the quadratic because this is 2 by 2. Okay, so it actually, in general, it should be a polynomial of lambda of degree n, where n is the size of the matrix. So for n equals 2, we just get that, and this means that the eigenvalues are 5 and 10. Okay. If the eigenvalues of this matrix is 5 and 10, then the negative value of the Q should be, because Q is negative this, then eigenvalues of Q should be negative 5, negative 10. But since we're trying to minimize this, okay, so we should choose the x corresponding to x as an eigenvector corresponding to the minimum eigenvalue, which is negative 10. So in this case, we're choosing x to be the eigenvalue. So this is a shortcut for eigenvector. EV is for eigenvector, EW is for eigenvalue. So we're looking for the eigenvector corresponding to the eigenvalue negative 10 of the matrix Q. Okay, so to that end, we just need to plug in x lambda equals to negative 10 and solve this lambda I minus Q x equals to 0. So for this x. Okay, so you can easily see that eventually there's this, and then solving for that x, we got that. Okay, so actually you can see any scaling of this x, any non-zero scaling of this x is also an eigenvector. Okay, as we know that eigenvector can be scaled by any non-zero constant, still eigenvector. So that's the eigenvector we're looking for. Okay, so because originally the problem did not require the x to have a unit length, so that's why you can feel free to scale the value x you have, and it doesn't change the ratio here. So any non-zero scaling of the x, of this x right here, is a solution, is a maximizer of this ratio, for this ratio. Okay. So that's all the maximizers for this function. Just all the non-zero scalings of the vector 2, negative 1.